Hello everyone, welcome to our channel. In today's video, we will design the layout of CMOS XOR gate and 2:1 multiplexer using Microwind. The practical is from VLSI CMOS Design Lab of JNTUH curriculum for ECE department. In VLSI CMOS circuits, 3 factors are considered during the design process. These factors are power, area, and operating frequency. In most cases, optimizing all 3 parameters is very difficult. Hence, designers tend to prioritize one design factor. Most VLSI CMOS EDA tools provide layouts optimized for one of these 3 factors. In previous experiments, we used the basic gate layout provided by the Microwind layout entry tool. We also used the PMOS and NMOS transistors provided by the DSCH Schematic entry tool. We utilize schematic to Verilog conversion and Verilog to layout conversion to implement area-optimized layouts for complex gates. In this experiment, we will use area-optimized designs for complex gates and circuits such as XOR gates and multiplexers. For both components, we will use the area-optimized design available in the DSCH Microwind tool. It should be noted that 6 transistors are used in designing the XOR logic gate. A 2-input multiplexer can also be designed using 6 transistors. The XOR gate includes 2 inverters and 1 transmission gate. Conversely, a 2-input multiplexer includes 1 inverter and 2 transmission gates. While simulating the XOR logic, we will observe that optimizing the area affects the minimum to maximum voltage swing of the output in the XOR logic, but not in the multiplexer design. Similarly, the power consumption of the multiplexer circuit is higher than that of the XOR gate design, although both include 3 PMOS transistors and 3 NMOS transistors. With this in consideration, let us start the design of 2-input XOR gate and 2:1 multiplexer. To begin, click on the DSCH icon to open the DSCH schematic entry window. Once the DSCH schematic window is open, select the XOR gate and drag the symbol onto the schematic window. Drag and drop the clock input in the schematic window. Drag and drop another clock source. Drag and drop the LED for the output. Use the Add Line option to connect the inputs and outputs to the XOR gate. Double-click on the icons to rename them. Rename the output LED to XOR Uniform. Rename clock 1 to A. Observe the timing of A. Rename the second clock to B, which is slower than clock A. Once completed, you are ready for simulation. Click on the Simulate button and, after some time, stop the simulation to check the timing diagram and verify the XOR gate's output. The output is 1 when only one of the inputs is 1. Now, you're ready to save the file. Save the file as XOR_v01.sch. Go to the File option and select Make Verilog File to create the Verilog Netlist. You will see that the module name matches the file name. Click OK. Navigate to where the schematic was saved to find the associated text file. Rename the text file and change its extension from .txt to .v, converting it into a Verilog file. Now, we shall create the layout using the Verilog file using Microwind. Open the Microwind program by double-clicking on its shortcut. Once the Microwind is open, go to File tab and click on Select Foundry to select the 0.35 micrometer foundry. Next, go to Compile tab, click on Compile Verilog. Go to the Verilog file by navigating to its location, selecting it, and clicking Open. After viewing options such as metal layers, click on the Compile button and then return to the editor. Notice that Microwind has created an area-optimized 6-transistor XOR layout. With all voltage supply and output configurations set, add a VDD connection to the in-well region. Proceed to simulation by clicking on Run Simulation button. View the output, which varies according to different logic cases. Observe that the output swing ranges from 0 to VDD. For some logic inputs, the voltage swing in less than VDD. This indicates that due to area optimization, voltage swing for some logic inputs has reduced form VDD. Check the minimum and maximum frequency by clicking on Frequency versus Time tab. Each time you adjust settings in Microwind simulation, remember to reset by clicking the Reset button. Click on FFT to view the operation frequency. Adjust the Y parameter values to view the maximum frequency. Click on Back to Simulation to close the FFT window. Press the Reset button to see the power consumption. Save the layout as XOR_V01 layout for future reference. This concludes our design of XOR gate using Microwind. Now let us continue with design of 2:1 multiplexer. Instead of designing the multiplexer circuit ourselves, we will use the multiplexer component from the DSCH tool of Microwave. Start by double-clicking on the DSCH tool. After the DSCH schematic entry window is open, you will find our multiplexer design in the symbol library. Drag the multiplexer into the schematic window. We will use 2 clock input sources. Drag clock input sources into the schematic window. We will add another clock source for the select line. Since we are designing a 2:1 multiplexer, there are 2 inputs and 1 select line. We will then connect an LED for output. Use the Add Line option to connect the various inputs to the multiplexer. The multiplexer's output is connected to an LED. Double-click on the components to rename the components. We will assign the output node the name as mux_out. Assign the name A to the first clock source. Note the timings of the clock source. For the second input, we will assign the name B. Note that the frequency of B is lower than that of A. We will name the select line as SEL. As you can see, the select line frequency is even slower than the 2 inputs. We will now run the simulation and after a while, check the timing diagram. Notice that when the select line is low, input A is sent to the output. When the select line is high, input B is sent to the output. After closing the simulation window, click on File tab, select Save As, and save our design with the name mux_v01.sch. Now, go to the File tab, click on Make Verilog file to create the Verilog Netlist. As we can see that the module name is the same as the file name. Navigate to where the schematic was saved to find the associated text file. Rename the text file and change its extension from .txt to .v, converting it into a Verilog file. Now we shall generate the layout using this Verilog netlist. Open the Microwind program by double-clicking on its shortcut. After the Microwind window is open, go to File tab and click on Select Foundry to select the 0.35 micrometer foundry. Next, go to Compile tab, click on Compile Verilog. Go to the Verilog file by navigating to its location, selecting it, and clicking Open. After viewing options such as metal layers, click on the Compile button and then return to the editor. Notice that the multiplexer design also includes 3 NMOS and 3 PMOS transistors, similar to XOR logic, which has 3 of each. All connections are already made, so we just need to click on Show Palette button and add VDD to the InWell region. We are now ready for simulation. Click the Run Simulation button. As expected, when the select line is low, one input is passed to the output, and when high, the alternate output is passed through. We will examine the frequency versus time plot, and as discussed earlier, each time we switch tabs, we must hit the reset button to see our design's operating frequency. By selecting FFT, we find that maximum operating frequency of our multiplexer design. Click back to simulation to come back to simulation window. Click Reset to check the power consumption. Click on Close button to go back to Layout window. Go to File tab, and then click Save as to save our layout as mux_v01.msg for future use. This completes our layout design for the multiplexer. Both multiplexer and XOR logic contain 6 gates each, but their outputs differ due to different configurations. Note that in the multiplexer design, there is no voltage swing issue. It ranges from 0 to VDD. However, the power consumption of the multiplexer circuit is higher than that of the XOR gate. We hope this video was helpful to all. Do not forget to subscribe our channel and hit the like button. Until next time, happy coding. Thank you.